All right, so what we're doing today really comes off of proof tip 12, which we didn't get to. And actually, if you go to proof tip 12, you'll see 4 problems on there. And those 4 problems actually are the ones that you're working on your homework with, the proof part of it. So that's where I got this from. Remember, unit 3, we went from proof tip 1 to proof tip 10. And then there's that 11 and 12. So 12 really fits in with what we're talking about today. With the perpendicular bisector theorem and its converse. We're going to give you a couple more theorems to use that will help with your proving and shorten some of your proofs. So first of all, let's take a look at this proof. It's definitely a doable proof for all of us. Let's just go through it. Okay, so you got the given, which is CD is a perpendicular bisector of AB, and that's given. And our goal is to show that AC is congruent to BC, or in other words, that this bigger triangle is isosceles. So it's not a segment, it's a line. So you see notice that CD in the picture has arrows as well. And there's a difference between a segment and a line. And perpendicular bisectors, if you really look, when we created them in GeoGebra, and you did that, you didn't get a segment, you got a line. It's okay if you say a segment is a perpendicular bisector too, but that's what the arrows are. All right, so you guys have a lot of background and experience with proving so far, so take it away. Give me a step that we need to prove this. Luis. Why? No, that's not the definition of perpendicular bisector. You have to look back at what that is. Yeah. Okay. We could say CD is congruent to CD by reflexive property. Of congruence. I'll mark that right here. But we do want to do what Luis was trying to do. He was trying to use the definition of a perpendicular bisector to give us some information. Perpendicular bisectors don't bisect angles. They bisect segments. So that's the key thing you got to know, right? Yeah, hope. And that's the segment that we're bisecting, right? So AD is congruent to BD. And why? Okay. Comes from the definition of a perpendicular bisector. And so whenever you hear bisector, you always got to think, is it an angle bisector or a segment bisector? And a perpendicular bisector is a segment bisector, not an angle bisector. Okay. What else do we need? Yeah. Okay. Angle ADC and angle BDC are right angles. And what we can do here is we can just bunch that in with the definition of a perpendicular bisector, because the perpendicular part gives us the right angles, right? The bisector part gives us the ADs congruent to the BD. So we can squeeze all that together in line 3. Good. You guys are doing awesome. Let me catch up to you. Let me mark the picture here. All right, so what's next? Yeah. Angle ADC is congruent to angle BDC. Why? All right, angles are congruent. Great. Let me pause here and let's just see. We have to write steps in here. So step 3 was relying on step 1. Step 4 was relying on which step? Step 3. Okay. Good. We're not there yet, but we're almost there. We can give donate another line here. I'm looking for someone that hasn't said anything yet. Yeah, Ty? Side angle size, congruence. Very good. Relying on steps. Which steps would do that? 2, 3, and 4. Nice. And anybody want to finish the proof off? What else do we need? You guys already answered. Looking for somebody that hasn't talked yet. Yeah, Donovan? Sorry, I wrote it wrong. You said AC? All right. So there we have it. This is kind of a standard proof that we maybe saw back in section 9 or 8 for proof steps, where we first learned about CP/CTC. But this is a proof that actually is popular enough where we have a name for it, and we call it the perpendicular bisector theorem. And so once you're able to prove something, you can call it a theorem. If you're not able to prove something yet, or you're just thinking about, that's not a theorem. But once you're able to prove it, then you can go to that theorem status. And so here's what the theorem says. If a point lies on the perpendicular bisector of a segment, then it's equidistant from the endpoints of the segment. And that's what we proved, but it's worded a little differently. So make sure we understand what it's saying here. So it mentions the word segment, so I'm going to put a segment here. So say we have segment AB. So if a point lies on a perpendicular bisector of a segment, so we need a perpendicular bisector of that segment. So if, I'm just going to draw a line through that segment. So it's got to be perpendicular to it, and it's got to bisect it, so cut it in half. And then our point, where would I put the point? If a point lies on the segment or on the line? So if a point lies on the perpendicular bisector, the perpendicular bisector is our line. So pick a point anywhere on that line. Put it here, it doesn't matter, I'll call it point C. Then that point is equidistant. What does equidistant mean? Same distance from the endpoints of the segment. So the endpoints would be like point A and point B. So the distance from C to A has got to be the same distance from C to B. And that's what we proved up here. It's the same picture we have here, except we started with a triangle here and we kind of made a triangle here. But that's what you proved. Now, because we're going to name this theorem, you want to know kind of what it says. And if you know what it says, it gives you the benefit of writing shorter proofs now. Here's what I mean. So now, from now on, if I gave you this proof, here's what your proof would look like. You say, okay, we got our statement and reason. You know how to write the first statement. CD perpendicular bisector of AB, and that's given. Oh, but it's a perpendicular bisector, so I could use my perpendicular bisector theorem. which says what? That AC is congruent to BC, and that's what I'm trying to prove. So I could skip all the way to the end of the proof. The AC is congruent to BC, and my reason would be the perpendicular bisector theorem. So instead of having a 6-step proof, I can reduce it to a 2-step proof. All right? Which saves you a little bit of time. Yeah. All right. So next I want to look at one more theorem, which is the opposite of this one, which is the converse of this one. And the converse is actually going to be more useful to you than this one. I'm looking at this one really to get to the converse. Because in the next unit that we're headed towards, we're going to have to prove a lot of things are perpendicular. And it's not always easy to prove things are perpendicular. And this is a kind of a key to help you get an easier proof for that. Yes, it's a perpendicular bisector theorem, but that perpendicular part is going to be useful to us. So this next one, let's try to prove here. We got our givens, so we're going to state AC congruent to BC and AD congruent to BD. That's given. Let's mark that up here. So we got AC congruent to BC, AD congruent to BD. And notice in our picture it says 90 degrees, but that's not given to us. So that really shouldn't be there. That's what we're trying to show. So we're trying to prove CD is a perpendicular bisector of AB. When you're trying to prove something a perpendicular bisector, you actually have to show two things. That it's perpendicular and that it's a bisector. We already have half of that. What do we have already? We have the bisector part. And that's coming from this right here, right? So we're done with the bisector part. The perpendicular part is the part we need. All right, so if you haven't contributed to the last proof, I want you maybe helping out with this one. What do we do here? Yeah. Okay, CD congruent to CD. Why? Good. I'm going to mark that here. All right, what else could we say? Elijah, did you help me with the last proof? Did you help with the last proof? No? Okay, what? Okay, so triangle what is congruent to what? By what? What? Good. That's relying on steps 1 and 2. Okay, so I'm going to take from there. So you guys proved the triangles are congruent. So now we have the freedom to take any part we want. And my focus is to show that these things are perpendicular. How am I going to show they're perpendicular? Well, I need to find a way to say that I have two right angles. So my focus is right in here, these particular angles. Okay? Yeah. That's definitely true, and so that's something we want to state. Before I state that, I'm gonna jump off of the congruence triangles, because when you get triangles congruent, then you get parts congruent. So what parts do you think I might want to say are congruent here? Yeah, those two angles are congruent to each other. We haven't said they're 90 degrees yet, but we'll start by saying, hey, they're the same. So angle ADC is congruent to angle BDC. And why is that, Lindsay? Good. Relying on step 3. Okay. And then what Ty was saying is that angle ADC and angle BDC are supplementary. Can you explain why, Ty? Okay, good. Do you remember the reason we haven't used this one a lot, but we did use it when we did a proof tip with perpendicular. And if anybody can help out too, that's nice. But anybody remember? Yeah, close. Yeah, it has to do with linear pair. It's not a definition though. Yeah, it's a kind of a theorem that says that two angles that form a linear pair are supplementary. Okay. Now from there, I'm going to do something that we haven't done. Okay. But I think what makes sense to you guys. Here's where we're at. Let me put some numbers here. So let's call this angle 1 and angle 2. And so from step 4, we have that angle 1, the measure of angle 1 is equal to the measure of angle 2, right? Let's just say measure of angle 1 is x, measure of angle 2 is y. So we have x is equal to y. And then in step 5 in our proof, we said that they're supplementary. What does that mean? They add to 180, so we have x plus y is 180. And so if I gave you this system of equations and said solve for x and y, what would you do? What's that? Divide 180 by 2. Why? So what's there's one step that you're seeing but you're not saying, and that is you're replacing one of these variables with another one. We're doing substitution, right? So maybe like take the x here and replace the y with it because they're equal to each other. And so you get, well, 2x is equal to 180. And so then divide by 2 and get x is 90. And because x is 90 and x is equal to y, then y's got to be 90, and we have it, right? So we see it, the algebra side of it. So to put that into words here, so I'm going to say angle ADC and angle BDC are right angles. And the reason I'm going to give, and it's not a reason you have to memorize or anything, we're just going to write it once and probably never use it again, but we're going to put it here, is two congruent angles that are supplementary are right angles, or end up being right angles. Okay, because they're congruent, that's our step 4, and they're supplementary, that's our step 5. So you see here the math side of things makes them right angles, and so this is relying on step 4 and 5. Now once we say that they're right angles, then we get our perpendicular, and that's where we were headed. We're trying to get perpendicular. So step 7, sorry I'm out of room, I'm going to put it over here, is that AB is perpendicular to CD. And the reason was, what do you guys think the reason is? Going to rely on 6. So in 6 we're saying that they're right angles there. Because there's right angles, why can we say they're perpendicular? Definition of perpendicular. Okay. And now I could say what I was trying to prove, that CD is a perpendicular bisector of AB because of which two steps? Which two steps tell us in our proof that CD is a perpendicular bisector? One, so step one right here, this is the bisector part, okay? And then the other part in 7, this is the perpendicular part, okay? And so we could say, hey, look at 1 and look at 7, and so we know it. What's the reason? Definition of perpendicular bisector. So that's there's no theorem or anything. We're just relying on definition. So that's step 1, 7. Okay. So we're just putting it here to show you, okay, it is true. Once you prove it, hey, we can call it a theorem. We don't have to prove it again, but we can use this theorem now to get what we want. Yeah. Okay, because step 4 says that they're equal to each other, right? Step 5 says that they add up to 180. And so if I substitute in x for y, I get x is 90. And x is equal to y, so y is going to be 90. That's fine. Okay. All right, so here's what we proved. The converse of the perpendicular bisector theorem says if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of that segment. Okay, so that's what we proved. What's going to be important for you is how to use that in a proof, and that's what the homework is going to be geared toward. And I'm going to get you started on the homework and show you what I mean by that. And if you look at the top of the next page, it spells out what you need to show perpendicular. So our goal is going to be able to say, hey, two things are perpendicular, and the method that we're going to use is we're going to show that we have a segment bisector, that we get something like this, which makes something like an isosceles triangle. Okay, and if we can show, so if I were to draw this, so we have this situation. So if I could show I got like an isosceles triangle, and then I have this line that cuts, that bisects. So you have a segment bisector, and you have kind of the isosceles triangle thing. Then we can use our converse of the perpendicular bisector theorem to say that, well, we have to have perpendicular. Okay, so that's kind of what we're needing and how we use it. And so let's use this in this first proof. So on number 1, we have a kite-looking figure. And with some givens, we're given that AB is congruent to CB. And we're given that angle ABE is congruent to CBE. That's all we're given. And based on that, we want to show that these diagonals are perpendicular to each other. Okay. And so I have a partial proof for us to fill out here. Anybody have an idea what number 2 is going to be? And you want to kind of look ahead to number 3, because number 2 is going to help you with number 3. Because there's multiple triangles in here, and you got to know, well, which triangle are we trying to work with? Okay. Do you have a feeling what? Yeah, Kaya. BE is congruent to BE. That's the one we want, because the triangle we're focusing on, or the two triangles we're focusing on, are the two smaller triangles. and BE is the side length that they share. Excuse me. So because of that, we can say that triangle ABE is congruent to which triangle? CBE. By what? Side, angle, side. Congruence, relying on steps 1 and 2. All right. Now, let's pause here and focus on what we're trying to show here and what I just said before we started the proof. So in the proof, we need a bisector. Do we have that in our proof yet? No. Okay. And then also the other piece we need kind of an isosceles situation. Do we have that in our proof? Yes. Where? That's this piece right here because we got this kind of isosceles triangle here, right? So we have the isosceles part in our proof. We need the segment bisector in our proof. And so that's going to help you with 4. Pick something that's going to help us get that part. You see what we need? What do we need? We have the triangles congruent, so which 2 parts do we want to say are congruent to each other? BE, no, what did you say? AE and EC, yeah. So AE is congruent to EC from step 3. And so that right there, well, is leading to the segment bisector. And so we say, well, you know what? Because those 2 are the same, then BD's got to bisect AC. Why? And this is how you finish the proof on your Unit 3 test. It's the second proof. What'd you write? Definition of segment bisector, which is relying on step 4. And so that is the second part we need. So we have the isosceles situation, we have a segment bisector. So if I have those 2 things in my proof, then I can call upon the converse of the perpendicular bisector theorem to finish it off. And so that is what we're going to do. 6. Otherwise, this proof would be much longer. I would have to say, well, then the angles are congruent and they form a linear pair, and because they're congruent and they form a linear pair, then we get 90-degree angles, and because they're 90-degree angles and they're perpendicular, I have to do all the extra stuff, and I get to skip all that stuff and just use the converse, which is saving some work. Okay, so we're going to say converse of perpendicular bisector theorem. And that's relying on what we highlighted, step 1 and step 5. Okay, so that's what we're practicing, and all 4 proofs here kind of are that flavor of proof. Okay. I told you I had some things to let you know here, right? So in the second proof, there should be a step between 1 and 2. Let's call it step 1.5. Okay. So that's one correction. Also, the coordinates here on number 2, I'm going to change on you. I tried these out and they weren't working nice, and so I came up with ones that would work nice for you to save you the trouble. Let me get those for you right now. All right, here they are. What I have in blue right here, A, B, C, and D. So A should be negative 6 root 3, comma negative root 6. B should be negative root 3, comma 3 root 6. C should be 6 root 3, comma root 6. And D should be 2 root 3, comma negative 6 root 6. Copy those down. Everything else is fine in the homework, but those are the two things that we need to make sure we fixed. And then there's a couple pieces on the homework that might get a couple of you like, ooh, I don't know what to do. And so I want to go over those things. It's stuff we've done before, but it may freeze you up, and I don't want you to freeze up on the homework. So I want to go over just a couple more parts after you get this down. Everybody have this down? Okay. So let's look at part C of number 1. And everybody find the slope of AC. Part of your homework anyways. Go ahead and find the slope of AC. Okay, so this is how you start. And we got to remember some stuff from Unit 1, right? When you subtract radicals, you have to make sure what's underneath the radical sign has to be the same. If I have radical 2 minus radical 3, I cannot do anything with that. And here we do have the same thing. And what is negative root 6 minus root 6? They're both negative. If it was one positive, one negative, it would be 0, but they're both negative. What? No. Negative 2 square root 6. So what we said before in Unit 1 is when we add or subtract, we're only add or subtract the coefficients, the numbers in front of the roots. We don't change the root when you add or subtract. So what's negative 2 root 2 minus 2 root 2? Okay. And then whenever you have a fraction, you simplify. So how do we simplify this? Okay, so we got the negative 2 and the negative 4, so it could be positive 1 over 2. So you can reduce that. Could I reduce the 6 and the 2? Can I like divide them both by root 2? You can. If they're both square roots, you can reduce them. So this would be like the square root of 3, and this would be the square root of 1. Now, 1 times square root of 3 is just square root of 3. Square root of 1 is what? Just 1, so this is really just over 2. So that's our slope of AC. Now, here's that wasn't the part that I was thinking would hang you up. The part that I was thinking would hang you up is, what's the slope that's perpendicular to this? So how do you find a perpendicular slope? Opposite reciprocal, so what would it be? Negative 2 or square root of 3. But there's a problem with that, isn't there? You can't have a square root at the bottom. Okay, so how do we fix that? Multiply top and bottom by square root of 3, and we get negative 2 root 3 over what? Over what? What do you get when you multiply root 3 times root 3? Just the 3. So here's what I want you to see. I'm going to highlight the two things. So we got this, and we got this. Do those look like opposite reciprocals? No, but they are. So when you're dealing with radicals, it may not be as obvious. Okay? And so what you're going to do, I'm not going to finish this, but you're going to find the slope of BD and hopefully get negative 2 root 3 over 3. Okay, and you will if you work through it. But in the future problems, you find your two slopes and you look at them and you're like, I don't know. So you're going to have to do what we did here, find the opposite reciprocal of one of them and then see if it worked out. Okay? So that's the first hang up I just want to make sure you didn't get hung up on. The second thing is using the distance formula with these crazy looking points. Okay? So let's find the distance of AB. So when I do that, you should have the distance formula memorized. If you don't, here's what I do. I take the two x values and subtract them to find the distance between them. Negative 2 root 2 minus negative, double negative, 3 root 2. And then I square that distance. Plus, I'm building like the a squared plus b squared equals c squared, Pythagorean theorem kind of thing. I want to find the distance between my y values, so negative root 6 and 2 root 6. So negative root 6, to find the distance you have to subtract, so minus 2 root 6, and square that. So got your a squared plus b squared equals that distance squared, but I don't want the distance squared, I want to solve for just the distance, so I take the square root. Okay, so double negative makes a positive. What's negative 2 root 2 plus 3 root 2? Just root 2 squared. Here, keep working ahead. God bless you. All right, guys, I will see you Monday. So if you want to take a look, this is what how it finished, okay?
Gary Garfield, please come to the health office. Gary Garfield, please come to the health office.
Yeah.